screen. Okay. So what you have is a step by step, how to size a load calculation all the way to 21 steps. 4 pages, 21 steps. Everybody understand what you have? 21 steps, 4 pages, how to size the feeders as well as the service conductors and the overcap protection device for the apartment building that we have. All based on an EC code book. Now your job, guys, is to build this in an Excel format with an actual data from the project that we have and come up with the size for the 4 feeders, for the 5 feeders that we have, which is apartment 1, apartment 2, apartment 3, apartment 4, and the common panel. These are the 5 feeders, and the main panel. Did you guys hear me? Everybody understand what the goal is? The goal is to size the main panel and the 4 apartments plus the house panel. Okay, so here's how the system goes. The way this is designed, you're going to have, you're basically going to have a service coming in and feeding. This will be my service. You're sizing the service. And then from here, you're sizing all these apartments, 1, 2, 3, 4. And then from here, you're sizing the, here's the 4 apartments, and from here you're sizing the house panel, and the whole thing is the main panel. One more time. You're going to have a main panel, or main meter center. We call it main meter center. That's going to be feeding how many apartment panels? 4 apartment panels right here, and a common panel or a house panel. This sheet will help you size all these 4 apartments. Why do we consider the 4 apartments the same, guys? You go to the largest apartment and use it as an example for the 4, instead of doing 4 calculation. One more time. This sheet will help you size, before we go ahead and start, help you size 3 things. Number 1 is the main panel. Number 2 is the apartment panels. Number 3 is the common panel. So Matt, when we were talking about the common panel, feed everything from the common panel, the house panel, they call it common panel, right? Or panel 5, we call it. How are you going to size that panel 5? Is it going to be 100 amp, 200 amp, 300 amp, 500 amp, right? That's what the load calculation is supposed to do. It's supposed to get you an amp size for your equipment. Can I guys get you to understand what this is supposed to do? But before I move on move on, I want you to understand that this sheet will size 3 things for you. The main panel, so under the column, under this column here, this all the calculation that you do here related to the main panel. Under this column here, or columns, all the calculation you do here is related to what? The apartments only. And under these columns here, everything that you do the calculation here is related to anything related to the house panel. Can I have thumbs up, Chad, that we understand? Because if I start talking about it, you're done. You don't understand it. There are a lot of things in this sheet. There are 3 things mixed together. You're pulling information from here. You're putting some of it here. You're putting some of it here, and some of it here, depending on, is it seen by the apartment? Is it seen by the common panel? Is it seen by the main panel? Let me tell you an example of how they do. So suppose that this panel, I have a heater. Remember that heater that we have, right? Do you guys remember the heater that you stuck in the apartment? These are in the common area. The heaters were in the common area. So they're going to be seen by which panel? Common panel. So this heater will be seen by the common panel. So when you load it, it's going to be right in here. Would it be seen by the apartment panels? Is it fit from the apartment panels? No. This is big 0, nothing here. Would it seen by the main panel? Yes. Because anything that comes into the house panel must go through first the what? The main panel, right? Like this light is fit from this panel right here. But this panel is fit from the main switchgear Dunwoody. So when I size the main switchgear, does this light count in sizing the main switchgear? Yes. even though it's not directly fed from the main switchgear, but it's fed from a panel that's fed from the switchgear. Any comments, any questions, guys, about this before we go ahead and start? Everybody understand what this sheet is supposed to get you? Okay, so now that we know what this sheet is supposed to get us, now let's go and just talk a little bit about it. All these are directly from NEC code book calculation. And you guys are supposed to, we're going to do an example in a second here. Okay, now, the first calculation that you do, guys, and step number one, can you guys see one here? General lighting. General lighting is from 220.12, section 220. The section in the secret book is 220.12, so that's what tells you about it. It says this number here is the square foot of the whole apartment, the square foot of the whole apartment, multiplied by 3 volt amp. Can you guys see the 3 volt amp? Multiplied by 3 volt amp, and then if you multiply these two by 2, this will give you a 12,000 volt amp. Now your job, guys, is to go measure the square foot of the apartment from the outside, double it, right? Why doubling it? Because it's 2-story. That will get you a number. Get you a number like 4,000 or 5,000, depending. This is an example. And then you multiply them. This will be seen under. This number will be seen under the main panel. Your apartment, guys, also have to have a square foot for it. So you take the square foot of the apartment, multiply it by 3, and that will get you the volt amp allocated for all the lights and the receptacle based on the NEC code book for every apartment. One more time. The first calculation related to the convenient receptacles and lights in the apartment. The code says, guys, for these convenient receptacles and lights, take a 3 volt amp, multiply by the square foot of the apartment, if you're doing apartment, of the common place, if you're doing common place, right? Of the whole building, if you're doing the whole building. Can I get thumbs up, chat, that we're 3 calculation doing? So you're going to take the square foot of the whole building, that'll get you this number. Then the square foot of the apartment, that will get you this number. And also another square foot for the common, and that will get you this number here. One more time. You take the square foot of the common area, multiply by 3. That will go under the common panel, the house panel. The square foot of the single apartment, the largest one, use the largest, multiply by 3, get you under the apartment, and take the whole building, top and bottom, 2-story. The square foot for the whole building, multiply by 2, and that will get you the main panel. Can I have thumbs up, Chad, for the lights? How to do the lights?
You should use the largest one, even though.
Yes. You know,
use the calculation for that.
yeah, we choose the largest one. Why would you choose the largest one? I'm going to split here. If you guys remember, we have 4 apartments. One of them has the largest, has an extra bedroom. We just use it because we standardize. You're not going to end up with one apartment 90 amp panel and the other apartment 100 amp panel. It doesn't make sense. So you choose for the apartment, you choose the largest panel. Can I have thumbs up, chat, about lights? Now lights is allocated for down lights. Let's go to the second one. Small appliances branch circuit. The small appliances branch circuit, guys, the NEC code book says that for small appliances branch circuit, you allocate 2 circuits for every apartment. 2 circuits for every apartment. Each circuit must have 2 circuits for every apartment. And all this is right here. Each circuit must have 1500 volt amp. So you take the 2 multiplied by 15, that will get you the total here for the small appliances. I want to remind you guys that these numbers. So for when you're doing the main panel, how many small appliances circuit you're gonna be doing calculation for? 2 for every apartment. 4 apartment, 8 of them. So when you're doing the calculation for this step, you're looking at 8. When you're doing the calculation for this step, you're looking at 2. When you're doing the calculation for this step, you're looking at what? 0. Are there any laundry small appliances circuit for the common area under the common panel? Did you guys feed anything when you did power? Did you feed anything for the small appliances circuit in the kitchen from the common panel? No. So that's 0. One more time. Small appliances circuit, guys, 2 per apartment. right? Based on NEC good book. So the whole apartment is going to have 8. So you 8 times 1500 volt amp. For each apartment is going to be 2. 2 times 1500 amp. For the common panel is going to be what? 0. Why 0? There's nothing. Is there in the kitchen? Common kitchen? No. Any comments, guys, about the small appliances circuit before we leave the small appliances circuit? Any comments, any questions? Laundry. Here's my laundry. The second part is for laundry. You guys can see the references for your laundry. The laundry is you have one 1500 volt amp, one 1500 volt amp for every apartment. There's one little problem. Do you guys remember saying any laundry room in the apartments? Were there any laundry room in the apartments? No. They were a common laundry area. And how many washing machines we have there? 2, right? And so what you do for each circuit, we have 2 circuits, you multiply this by 2, multiply by the 1500 volt amp, and that will get you under the common area 3000. The example I have here is example, guys. The numbers are not right. Did you guys hear me? The numbers, like number of circuits, are not right, and I did it intentionally because I want you to find the right number. Did you guys hear me? So under the laundry, we have 2. Now, here's my question, Adam. Do you think, where did you feed the laundry from? Did you feed it from the apartment panels or from the common panel? You guys remember? Common panel. So under the apartment panel, this step will show as what? Big fat fluffy 0. Under the common panel, it will show also as what? 3000. Did you guys hear me? So every load is going to count twice. Once under the main panel and once under either the apartment panel or the common panel, depending on is it fed from apartment panel or is it fed from a common panel. Karen, any questions, any comments? So that's your laundry. So now, Matt, we accommodated for all the lights and conveyor receptacles, load-wise. We accommodated for all the small appliances circuit in the kitchen. That's what the code says. 3, we accommodated for the laundry circuit. Okay? Now, step number 5, guys, says add them all up. You're going to add them up. Add all the 3 steps that you did. That's it. You just add them up, whatever. Under each step, they're going to be added up under each step. Step number 6, you're going to apply demand factor. You're going to apply demand factor on them. I will go through how to apply the demand factor in a second here. We have an example for you. But just a quick, the first 3000 volt amp leaving a load, anything higher than 3000 amp, cut it by 35. That's from table 220.42, 220.44. So you have to demand them. Why do we demand them, Karen? We demand them because it's highly unlikely that all the receptacles, all the lights, all the receptacles in the kitchen are highly unlikely they're going to be running at the same time. So they demand it. Any comments, any questions up to step number 6? This is, guys, involved a little bit. Comments, questions. Okay, so we accommodated for the number 6 is the demand. So this is my demand. Number 7, guys, ranges. Now we need to go to the ranges. My ranges, you're going to take all your ranges, multiply them by how many demand factor you have. What demand? Remember how we did the range calculation? And you're going to add them under MP or wherever they sit. So for the ranges, how many ranges do we have? 4. Each one of them is 8,000 volt amp. How do I know? The sheet that I gave you guys has them. So for 8 ranges, add them under the main apartment. You can do the calculation for 8 ranges under the main apartment. And also for 8 ranges, for 1 range under each apartment, and you do the calculation. Like we did ranges. Derate them and add them. That's the calculation to account for the range load. Any question about the range? Any question, guys, about the ranges? Right underneath it, guys, and by the way, I'm going step by step in a second after I walk you guys through this one of all this calculation for an apartment building. This is just a guide for our project. For actual calculation, I'm going to be doing it step by step in a second. Electrical dryers. Here's my electrical dryers. The NEC code book, guys, we have two dryers, 500 volt amp. They're all fed from the main panel and from also the apartment panel. Did you guys hear me? I can't emphasize, when you do your load calculation, you have to ask yourself, first, I know this load is fed from the main panel. The second question, is it fed from the apartment panel as well? Or from the house panel or the common panel? You guys, every single load that you put there, you have to ask yourself, I know it's fed from the main panel, but is it also, where is it fed from? Next, apartment panel or house panel. Okay, for dryers, we take the two dryers, multiplied by 2 from the NEC code book. How to do the math on it? It's coming in a second here. We're going to be doing an example. Number 9, step number 9, furnace. Furnace, step number 9, guys, it's called electric furnace, air conditioning, that's heating and cooling. You take the largest of your heat and cool. So here's the largest of my heat and cool. And you put it under the main panel and also under each apartment, under each one of these apartments, because it's feeding the apartments. Any comments, guys? Can you guys see what I'm doing? I'm accounting for every single electrical load fed from these panels. Who cares? That's how we size that panel that you're looking at here, and the main panel and the feeders. Ultimately, guys, you as a designer, they're going to come to you and they say, is this going to be a 400 amp panel or a 6,000 amp panel? Right? How are you going to accommodate? Here's the step-by-step how you do it in an Excel format. We have a sheet like this, Adam, for residential, and we have sheet for commercial and one sheet for industrial. Did you guys hear me? And typically, because they're involved, what I do, I give you the sheet as in a PDF file, because for you to come up with that format sheet, it will take us more than a week, man. It just so to focus your mind, here's the sheet, how it looks like. Your job is to fully understand it, what the sheet means, and why do we allocate it for each one of these loads, and apply it for our project. Okay. Step number 10 is add them all up. So we added all these. Can you guys see? Added all these steps ahead. So now this is page 1. Let's go to page 2. When it comes to page 2, so what we did, Karen, is we accommodated, or we accounted for the lighting load and the convener receptacle lighting load for the kitchen receptacles, small appliances, for the laundry, for the heating, for the cooling, heating and cooling, we choose the largest. We accommodated also for the ranges and the dryers, right? What else left in the apartment that we need to pay attention to? What else left based on the NEC code book? Step number 11. There's a term that's called fastened in place appliances, guys. Fastened in place appliances. These are commonly used appliances in dwellings, only dwellings. A good example of, they call it the water heater, dishwasher, food waste disposal, and microwave. These guys are fastened in place appliances. I need to accommodate for them. Garbage disposal is another one. Garbage disposal. So you add them all up. The question would be, Adam, where am I going to get the volt amp for them, Chad? The sheet that I gave you guys at the end has all the volt amp for these equipment. Otherwise, good luck. I mean, how would you know? Can you guys see that sheet? Has all the volt amps for these equipment. You're going to add them up, and then you apply step number 12, the apply demand factor. Because you guys are doubting Thomas, here is the reference for each one of these steps from NEC code book. So you add them up, and if there are, if there are, can't remember, was it 3, what did we see, how many of them, 75 blood demand factor, 4. If there are 4 or more, then you apply a demand factor of 75%. Adam, where does it say that in NEC code book? This is from Article 220.53, or section. Can I have thumbs up, Chad, that we fully understand that the small appliances, fixed in place appliances will be accounted for in step number 11 and would be derated in step number 12. Does that make sense? Yes, no? Okay. So you just add them volt, you multiply them, you add them up at face value, and then you derate them 75%. Okay. Step number 12 is compound, total compound. You add them all up, add everything else. Okay? Add them all up. And that's what you're going to come up under each one of these steps, what you did. That's just adding everything that you have done so far and tells you which steps. Step number 14 is accommodating the motor load. Motor loads. All your motors are going to be accommodated for. They call them motor load. From for Article 430, 250, 220.50. I have a sump pump, a laundry exhaust fan, a bathroom exhaust fan, a pool heater, a pool pump, a garage door opener, and a furnace. All these guys are motors. Can you see, Karen? All these are motors fit from this apartment building that must be accounted for when we size the panel, the main panel, as well as the apartment and the common panel. So you add them all up right here, face value. Add them up face value. Sorry? No? I thought you. Okay. And then you have to pull them under whichever are they're all under the main. But are they under the apartment? The one under the apartment is going to go under the apartment. The one under the common is going to go under the common. Any question, guys, about sheet number 2? Sheet number 2. So now we accommodated for all the fasten in place appliances. And who came up with the fasten in place appliances? That's a code. You know what I mean? That's why for you guys to come up with all these together, it would be a little bit harder. That's why we always, Adam, I don't know, you guys, when you did the residential, you have a sheet. Typically, we have a sheet. Were you given a sheet to do residential calculation? A lot of people, it's a good start to start with a sheet to focus your mind. Okay? Now, I want to remind you, the numbers here might not be right. So your job is to go check the numbers based on what I have given you. Did you hear me? This is just a guide, and intentionally, otherwise might as well do the whole calculation for you. This is a guide. It will give you how are you going to do it. You have to plug the number. If in doubt, you ask me, Chad, I don't know where this load fits. Okay? But for the most part, that will give you 95% of what you need to build it up. There will be 5% kind of gray area. Always in doubt, ask me. Okay, that's sheet 2. Let's go to sheet 3, guys. Sheet 3, for the motors, the smarter than Chad decided for motors, they take the largest motor and add 25% on it. So if you have 10 motors, when you size the feeders and the service for them, you take the largest, fattest, fluffiest amp-wise motor and you multiply 25%, a bit 25%. That's how the code tells you. So that's where the 25%, only on the largest, not all of them. Now I accommodated for all my lights. Then grand total, here's my grand total. That's a total. That's the whole step. Then this is the total for each one of these buildings. Adding everything. Then this is the single most important value that you're going to get, guys. Then step number 16 gets you the amplicity of ungrounded service entrance conductors and feeders. You divide it by 240. Why do we divide by 240? Why do we divide by 240? Because the voltage system is 240. And ladies and gentlemen, that will get you an amp right here, an amp size for equipment. I have 191. My next standard is 200. Again, this is an example. That's how you're going to size your panel. Now, I can't emphasize, when you are at this level here, guys, you're going to have 6 sizes. 6 sizes. 4 apartments, so it's going to be P-1, P-2, P-3, P-4, P-5, right? These are the 5 panels. 4 of them are the same size, and 4 of them, these 4, right, are going to be the same size. This one is going to be the common, and then you're going to have a main panel. That's the 6th. The main panel is the big one that feeds all of them. Am I making sense? Everybody see what we have a main panel that feeds 5 panels, and 4 of them are going to be the same size. The 5th one is going to be different. The 5th is the common load panel. That's it. Now we size the panel. From size of the panel, guys, you're going to size, when you size, I have an example with you now. When I say I sized it, You size three things when you size it. Number one, the panel size. Number two, the overcome protection device size. Number three, the conductor size. Like you have been doing with me when they say size is not enough. Oh, what did you size? I came up with a 100 amp panel, 100, say 100, 125 amp panel, single phase 240, 60 hertz. That's going to be fit from protected by a 125 amp circuit breaker. That's going to be landing on it, four conductors, number 4 out. Done. That's what sizing for each and every one of these apartments. Again, 4 of them are the same. So technically, you're sizing really three things. The common panel, all the apartments because they're all the same size, and the main panel. Why did I make them the same size? Could I have not made them the same size? Yes. Why would I have make them the same size? When you design a building, guys, the worst thing that you could happen is here's a 50 amp panel here, and here's a 60 amp panel here. That's called splitting hair. You want to standardize when you get into a building. So if one of them is 50 and the other is 60 and the other is 90, make 100 amp panels all across the whole building. Standardize your design. They call it standardize. So you walk into this building, they're going to be most likely each one of them is 100 amp panel for the apartments based on the calculation. Okay, any comments, any questions? Now, step number 17, the neutral conductor. Do you guys remember how the neutral conductor can be derated? When we have a neutral conductor, the two hots can be the same size. The neutral most likely will be smaller because not everything needs a neutral. So then step number 17 will help you size the neutral. This is moving forward here. This is just to size the neutral. So they take all these steps that we went through and we grab them. For example, for the range, you multiply by 0.75. For the dryers, 0.75. Everything else for the lights and the receptacles, phase value. You do the same calculation, Matt, exactly step 1 through step 16. Step 1 through step 16 for the neutral. Starting at step 17, it will get you step 1 through step 16 again for the neutral. Here's the funny thing about the neutral. If the load is 240, you drop that load, doesn't count. I have an example for you in a second. If the load is 120, it counts, unless the code tells you otherwise. Did you guys hear me? When you size a neutral, anything that says 240, 0, it's not going to need neutral. Doesn't count when it comes to the neutral. If it says 240, if it says 120, it counts because it's 120, right? So here's all the ranges and the dryers that need sequence book because they need a neutral. They need a neutral, even though they're 240, 120. So the code says cut them by 75%. That's a good. And then we do all the calculation here, guys. The same calculation for the neutral. Can you guys see right at the bottom here? We have the motor load only, but look which motors are we accounted for. Only the motors that are running at 120. Anything that's running at 240, when it comes to the neutral, big fat 0. Okay, so we did the same calculation based on the neutral. That's what you did, guys. Starting at 17. Okay, so we did add them all up, then divide again by 240. Now, why would we divide? The neutral is 120. When I added all the volt amps for the neutral, why did I divide by 240? Because remember, there are two hots and a neutral, and your job is to balance the loads between the two hots and a neutral. So ultimately, they will be fit from the 240, right? Because half of them will be on one leg, the other half will be on the other leg. You know, so they might be 60-50, but that's what ultimately you're going to end up. So you divide it by 240. Ladies and gentlemen, this size will be the size of your neutral. These sizes will be the size of your neutral. Okay, now we're done. At the end, you need to go and find the ungrounded conductors, size the ungrounded conductors. Then you size the neutral. Then you need to size the grounding electrode conductor. Then size the raceway for this system. Can I have a thumbs up, Chad? We at least understand. Guys, I know it's a lot of information. So I'm giving it to you. You're going to look into it. You're going to build it in an Excel. It will take you a couple of days monkeying around and building it in Excel. But I want to give it to you. This is doing the week 7. I want you to start right now on it as you do your low voltage. building it in an Excel sheet. You know, are you good with Excel? Everybody's good? Math, did you do Excel? The Excel, guys, the Excel math in it is really not hard. The hardest one will be F, using the F. If then I can help you with doing that math, but most of it is you hit equal in Excel and then add and multiplication in Excel. I would say 90% of this is addition and multiplication in terms of math. There is one where you have to say if this then, if then. I don't know if you guys, I can help you with that one, how to get the math for it. Other than that one, everything is sum. There's a function that's called equal sum cell 1 through cell 15. And when you reach the math, I can help you. If you want two cells to be equal, just say hit cell 1, go to cell 1, need to be equal to cell 3, equal cell 3. So these two cells will be equal. The amount of math is really minimal in Excel. Typing, you know how to use Excel. These are all, every one of these is a cell. You know what a cell is, right? In Excel. Everybody use Excel, right? Math, you probably is the least. So the rest of it is just all that fancy stuff that you see is really just formatting the stuff, making it squares and making tables out of it. This is your load calculation for this project. This is your load calculation for this project. Any comments, any questions? You guys have it online. You should start building it in an Excel format. Now, having this handy, I'm going to go, guys, and start an example using, I want you to keep it handy, though, and we're going to go apply these rules. I'm going to give you, should we take 5 minutes because I need your full undivided attention. Should we take 5 minutes, just stretch a little bit? And then when you come back, we're going to take an example and use it by hand, applying the same rules that we've just went through by hand, so get you to do the math, right? Shall we? 5 minutes, please. Thank you. Okay, so let me put this one right here. Okay, here's the situation. Let me read my nice handwriting for you. Residential load calculation. Example number 1. We have how many units? An apartment building with 30 units. Cool? Riser, like one in downtown Minneapolis. Each unit, so 30, how many units do we have? We have 30 units. Each unit, so it's an apartment, 30 units. Each unit has 1,000 square foot area. Cool? Each unit. The voltage that we're feeding this apartment from is 240/120. Each unit, did you guys hear me, has an AC of 30 amp at 240, AC unit. I have a heating, electric heating, 10 kW at 240. A range 16.5 kW, also at 240. If you guys want to add at 240, this is also at 240. And a dryer at 240. A dryer of 6.5 kVA at 240. A garbage disposal of 1.5 kVA. If I don't tell you it's a 240, it's always assumed to be what? 120. Thank you. Unless I tell you the load is 240, it's always assumed to be a 120. Right? So a garbage disposal of 1.5 kVA, 120. Dishwasher 1.2 at 120. Heating, I have a heating of 5 kVA at 240. A pump, this pump is also running at 240. 7.5 horsepower pump, that like some pump in the basement of that apartment, so it pumps the water out, and it's sitting at 7.5 horsepower. These are all the loads that's coming from this riser. This riser, here's my riser here. How many? 30. So let's just say 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and 8, 9, and 10. There's an apartment, and if you say cut it by 3, isn't that a nice apartment building? So each apartment, each floor has, say, three apartments. Each floor has 3 apartments. Imagine that the architects designed it this way. It doesn't have to be this way. So we have 30 apartments in a big riser, and your job is to design the service for it. The apartment that we have is how many? 4 apartments. Very similar. Any comments, any questions, guys, before we go and do the calculation? Everybody got the idea? So your job and my job is to size the following. We need to size the service entrance conductor, the service panel, and the neutral, as well as the overcome protection device. So we need the service panel size, the overcome protection device in the panel, the service ungrounding conductor, the hots, and the neutral. 4 things we need to size for that baby. Any comments, any questions, guys? Everybody understand what we have? All right? Matt, can I move to the next one? Okay. All right, now. All right, the first step, guys, that you need to do is step number 1. By the way, these steps are coming from the sheet that we were just walking you through. General lighting. General lighting. I'm going to go to my general lighting. So for my general lighting and receptacles, general lighting and receptacles, table 220. I'm going to be flipping, guys, into the tables. Here's table 220, Mac, because you probably haven't seen that. Here's table 220. Can you guys see that? 220.12. Do you see where it says dwelling? Everybody can see in the NEC code book where it says dwelling. 3-volt amp. Can you guys see that? Dwelling 3-volt amp right here. That's where this information is coming from. Cool? Okay. Now let's go back and so we know what this table is. So we remember we're sizing it for the whole apartment. So we're going to take 3. Everybody knows why 3. Here's my 3. Multiply the 3, the general lighting and receptacle, by 1,000 square foot, and multiply this one by 30 units. Right? So 1,000 square foot, because there's 30 of them, 1,000 each. When you multiply them, you end up with a healthy 90 kVA. 90 kVA. Where did they come up with the 3, guys? From table 220.12. Where did they come up with the 1,000 and the 30 units? That's what the example is. See, straightforward, no gimmicks, nothing. No gimmicks, nothing. I have to erase that one here. So I'm going to, so this is for lights. Okay, so that's for lights. Small appliances. Small appliances, branch, circuit. Small appliances, branch, circuit. Yes, sir.
Why does it go from 1 to 3 to 4? Is that just
2 is following that one. If you look at 2 here, that sheet that we have, I think it's just to follow what we've been doing, because I don't want to
okay.
follow the format here. 1, 3. 2, you know what 2 is? 2 is to find the branch, how many branch circuits you need in the apartment building, and we care less about the branch circuits here. I'm following this format. Okay, good point though. I'm following this format. Thank you. What happened to 2, Chad? 2 is the branch circuit, and we're not interested in the branch circuits at this point. Okay, so for small appliances, guys, 220.52a, if you guys go to 220.52a, here's the NEC code book, 220.52, all the way 40, 52, 52a. 220.52a. Here you go. Math, especially math. This is where this information is coming from. 150, can you guess 1500 ohm for shall be calculated for small appliances at 1500 volt amp. For laundry, right underneath it, 1500 volt amp. For these here's my small appliances circuit. Can I guys get you to see that? Everybody can see that? These are where this information is coming from. Let's take a snapshot at it. Okay. All right, so now we got these, and I like to to go back. So we got, everybody knows where the 13, so for small appliances, every apartment is going to have two small appliances circuit by code. Where does the 2 come from? Small appliances, 52A, it tells you need 2 circuits. Not Chad. Good. Multiplied by 1.5K. Where does the 1.5 come from? From 220.52A. Multiplied by 30. Where does the 30 come to be? Where does the 30? 30 units. And that will get you 90 kVA. 90 kVA. 90 kVA. Same thing for laundry. Laundry. Every apartment is going to have a laundry circuit. Where did the 1 come from, Karen? The laundry circuit 220.52B. 220.52B will tell you 1 circuit for laundry for every apartment or every dwelling. Multiplied by 1.5K equal, oh, don't forget that multiplied by how many of them do I have? 30. 30, and that will get you a healthy 45 kVA. 45 kVA. 45 kVA. 45 kVA. Any comments, any questions, guys? Everybody sees? Matt, can I just pick on you? And can you see first the association between these numbers and the sheet that I just walked you through, step by step, right? Everybody can see that? And how to do it now, instead of doing it for me, when you do it for the project, instead of doing the math, this is the math that you're going to do in Excel. You take the cell 1, multiply it by cell 2, multiply it by cell 3. In cell 1, you're going to put the number 1. In cell 2, you're going to put 1.5. In cell 3, the number of units, and that's what you're going to get. Can you guys see that? That's the math that you're going to be putting in Excel for Chad. Okay, everybody can see that? Yeah? So let's, let me go back and, okay, we got these. I'm going to go and take a snapshot at my, just to be consistent here, at my my apartment, this one. I like to take a snapshot. If you guys have not highlighted this table, please go ahead and highlight this table. Where's my dwelling? Here's my dwelling, and here's the 3. When we started the 3 volt ampere square foot, let me just take a snapshot. Capture. The reason why I do that one, because this will be PDF for you in the network. So for review, you know where I went through. In our industry, guys, you can see anything you want as long as you substantiate it with an EC code book, right? You're gonna. So here's where we got that one. Okay, now let's go. We got this. We got this. Okay, now it says add 1, 3, and 4. Now step number 5. Add 1, 3, and 4. So we'll go add them up. Here's 90K, and here's another 90K, and here's 45K. Add them up, and that will give me 225 kVA. This is just adding them up. Cool? Adding them up. Adding them up. Just adding them up. Oops. This is, what was the small appliances and 1 laundry. Laundry circuit. Edit. Undo. Okay. There you go. I just want to leave that one here. Just to be consistent. So here you go. To 225. Any comments, any questions, guys? 225 kVA. Now, apply the demand factor. I'm going to take you guys to the demand factor. Now, remember that demand factor that we're going to be doing? Let's go to the demand factor. Let's go directly into my demand factor. Here's table 220.42. 220.42. Here you go, right in here. 220.42. Let's go look at this table. If you have not highlighted this, please go ahead and highlight this table. This is my demand factor table. This is the one that we're going to be interested in. Why? Because we're doing dwelling. The demand factor, because it's highly unlikely these apartments guys are cooking at the same time, all the lights and everything else, they allow you to chop it down, cut it, reduce it. Okay, they say the first 3,000, leave them alone, 100%. Don't touch them. Anything higher than 3,000 up to 120, cut them by 35. Anything higher than 120, 120,000 of course, cut it by 25. Now let's go do the math. That's the math that we're going to be doing. Can I have thumbs up, Chad? We fully understand that's the math what we're going to be doing. Now let's go do it. So that's where this is coming from. Let me take a snapshot of this baby. Capture. Why did I highlight dwelling? Because we're not doing hospital, are we? We're doing an apartment building. Okay, so let's go. We got that one. We got that. Okay. So demand. Let's go apply our demand. Okay, for the demand, look what I want you guys to pay attention to the demand. Take the 225 kVA. Okay, now, Matt, based on the rule, it says the first three, leave them alone. Here's the first three. 3 kVA. Do I touch that 3 kVA? Don't touch it. Next. The next you take 120 minus 3 and multiply it by 0.35. Why 120 minus 3? Up to 120, guys, between 3 and 120 kVA, the code, if you look at the sheet, it says cut it by 35. That's how the math is. 120 minus 3. Then you take 225 minus 120. Cut this one by what? Cut this one by 0.25. And then do not forget to add them all up. Add them all up. So when you add them all up, you're going to end up with 70.2 kVA. This is the single most important value that you're going to be using. One more time. Let me highlight a couple of things, guys. Can you guys see the 120 here? And the 120 here? And the 3? All these three numbers that are highlighted, Karen, are coming from the NDC code. The only number that's not coming from the NDC code book and this 3 at the top here. One more time. The first 3, leave it alone. Then take 120 minus 3, give you 117, multiply by 0.35. Take the 225 minus 120, cut it by 0.25, add them up. Can I have thumbs up, Chad? We fully understand what you're doing. Matt, this is probably the most complicated formula you're going to do in Excel sheet. Because you have F then. You're going to use the F then. I'll help you to do that with Excel sheet. Before we do it though, I don't know if you guys done it when you were with us in dwellings. If you have not reached the step 3, maybe because your load was not higher than 120. If your load is not higher than 120, you do not need to go to step 3. Did you guys hear me? Only you go to step 3 here if your load is higher than 120. Is my load higher than 120? 225 is higher than 120. Before I leave the steps, does every one of you guys know how to apply it? The first 3, leave them alone. 120, where does the 120 came from? From my code. Minus 3 from the code. Multiply by 0.35. 225, that's my total. Minus 120 from the code. Cut by 0.25, done. So here's the irony, yes. I went from 225 kVA load down to what? 70.2. Do you guys appreciate? I want you to not just understand, appreciate what the demand factor is. You know what that makes to you? That have just taken your size of the panel from this size into this size. Based on the diversity of the load. It's highly unlikely that people are going to be cooking and running their air conditioning and their lights are on and their stereos are on, everything at the same time. That's human being behavior, right? If all of us pick up the cell phones and start calling at the same time, what's going to happen to the cell towers in the area? You overload them, right? So that's highly unlikely is this going to happen. Typically, do you use your phone when everybody in the classroom is using their phone? What's the likelihood that this could happen? only in catastrophe, like September 11 or something like this. All right, so this step number 6. Can I get you to understand? Step number 6 is also tied to the Excel sheet PDF file that I showed you. That's how we're going to do it. Cool? The only thing we're going to do is we're going to do this math in an Excel format. Can I move on? Yes, no? Okay. All right, so let's go to step number, we got that one. Let's go to step number 7. Okay, now, this is what you need to size, guys. And I already sized that one for you. We need to size, for this apartment, we need to size the panel itself here, that panel. I will make a copy for you guys for this one. We need to size the overcome protection device and the conductor. So you hold on this one, I'll make a copy of this this sheet for you. That's what we're trying to achieve out of this system, is sizing the service and sizing this service. I'll get back to you. Hold on this one. I'll make sure I get you a copy of it. Okay, let's go to ranges. Now ranges, let's do range calculation. Step number 7, range calculation. For range calculation, guys, how many ranges do I have? I have 16.5 kVA range. Do you guys remember how we did the range calculation? Table 220.55. There's 30 of them. You're going to go to under C. Under C for 30 of them, guys, you're going to find 45 kW. And the demand for them is 45 kW. Cool? Under C. Under C. Let's go directly to that one. I know we did some, here's the table that you're going to do. Okay, here you go. How many of them? I have 30 of them. For 30 of them, 30 is right here. Okay, and we are going to have, for 30 under C, you're going to have 45. Did we do that one for 30 of them? We have 5 plus 1 kW for each range, 45. How did they come up with 45, guys? How did they come up with 45? If you look at this range. Okay, for 30, 26 through 30, this is the math that you need to do. So it says 15 kW under C plus 1 kW for each range. How many ranges do I have, gentlemen? 30. Equal, add them up, 45 kW. Everybody understand where we came up with the 35? Can I have thumbs up, Chad, that we fully understand where the 35 came to be? It's 15 kW plus 1 kW for every one of them. Okay, so now it's 45. Okay. Now, as long as we're here, guys, I want to remind you, if they're all the same size, remember how you have to increase the average by 5%? That's not number 1. So now that we are there, we found the 45. Okay, go back. Okay, so that's your start point. Now, the next thing that you need to ask yourself, my friends, is had the range be less than 12, we're done. Do you guys remember the range calculation we did? I don't want to go into the details on that. But since this is more than 12, then you have to do another step. You take the 16.5 minus 12. Where does the 12 come to be from the code? We'll give you 4.5 kW, which translate, you go up to 5 kW. Excuse me. Then, for every kW more than 12, you increase the demand by 5%. Every kW more than 12, 5 kW, increase the demand by 5, so your increase is going to be 25%. And finally, you're going to take your demand load is going to be 1.25 multiplied by 45 kW. And that will get you a healthy, right in here, a healthy 39.9 kVA. 39.9 kVA. Any comments, any questions? That's range calculation. Now, Matt, you wonder why did Chad make us do all the calculation for ranges? Because you need to use them when you size your service.
How'd you get the 39.9? 31.25 times 45. 56.25.
Well, I invented new math. Or I made a mistake. This is for the neutral. It's coming. I just looked at the wrong one. It should be 56. Thank you. 56.3 kVA. I'm one step ahead of myself. I'm sizing for the neutral. I have two numbers here. Looked at the wrong one. Yeah. Good point. When you multiply a number more than one with a number and you come up with a less than that number, you invented new math or you made a mistake. Typically, you made a mistake. Okay, 56.3 kVA. Do you guys remember what we did for the range calculation? And I know we spent some time doing grade calc. All right, let's go to step number 8, shall we? Step number 8. Look at our ranges. Okay, we did the same calculation here. Okay, step number 8 is for the dryers. The dryers. Do I have a step for, okay, dryers? For dryers, I would like you guys to go to this table. Let's go directly to the table for the dryers. Here's the dryers. Right here. Demand factor for dryers. If you have not highlighted this table, please do so. If you have not highlighted this table, please do so. Here is my dryer. The table for the dryer. How many dryers do I have, guys? For dryers, I have 30 of them. Okay, where's my dryer? I have 30 of them. 30 would be right in here. Can you guys see that? Is that where 30 is? 30, right? Now, it says 35 minus 0.5 for each dryer exceeding 23. So how are we going to do this math? Right? How are we going to do this math? One more time. 35, I have 30 dryers. 30 dryers will put me right here. So then when you apply that rule, it says 35% minus, so you can see minus 1 minus 0.5% times, open brackets, times the number of dryers exceeding 23, so that 30 minus 23. This is how we translate this math. One more time. It says 35% minus 0.5 for every dryer exceeding 23. How do you translate every dryer exceeding 23 in math? You take the number of dryers, which is 30 minus 23, and multiply it by 0.5. And by the way, don't worry about the percentages in the calculation, because the answer will be in percentages. So, do you guys hear me? The percentages here, when you do the math, don't worry, don't look at the percentage. Your answer will be in percentages. Okay? Everybody can see that one? The answer here should be, and I'm going to do it in detail, should be 31.5%. When you do all your math, let's take a snapshot of that baby and go back and do it a little bit more details. Okay, which did we get? No, not this one, Chad. Okay, take a snapshot. Went too fast. Capture. All right, so we got that one. Minimize this. Go up here. And okay, so here's how you do the math, guys. You take the, where are we here with dryers? 6.5 kVA. Take this one to table 220.54 under 30 dryers. Here's what you take. You take 35% minus 0.5 times 30 minus 23. then give you a 35% minus, this is percentage here, minus 0.5 times 7, and this is all equal, and when at the end here, 35% minus 3.5%, and the last thing should come up with 31.5%. That's your derating factor. Okay, gentlemen and ladies, or ladies and gentlemen, you're going to take the 6.5 kVA, multiply it by 30. Why 30? Multiply it by the rating factor of 0.315, and that will get you a healthy 61.4 kVA. That's your demand for the dryer. That's your demand for the dryer. Any comments, guys? Any questions? Any comments? Any questions? Your demand for the dryer. Now, can I get you guys to understand that the code for dryers, Adam, the code says, if your dryer is less than 5, go ahead and use 5. So had this dryer size was 4.5, you have to use 5. If you don't believe me, you're going to go read 220.54. Less than 5, use 5. Are we less than 5? No, we're 6.5. Then use the 6.5. What I'm referring to, guys, is this calculation here. This one is minimum, min 5 kW. Might have to write yourself a note. Minimum 5 kW. If it's less than 5, you have to use 5. Shall we move to 9? When you guys have a chance? I do have another dryer example for you, nothing related to the project, because I thought we didn't touch on the dryers enough. So can I guys have your attention? I'm going to do another dryer example, has nothing to do with the project here. So here's the dryer example that I always use. Okay, no, not this one. Let's go here. Okay, now, Karen, I have extra dryer example. That's extra. Had nothing to do with the load. Just how to do the dryers, because we haven't done enough. I have 40 dryers. Each one of them is 5.5 kW. Okay? How are you going to use them? If you guys go to 40, it says 35% minus 0.5%. Multiply this one by 40 minus 23. And that will get you 35% minus 0.5% times 17, and then 35% minus, I'm going all the steps, 8.5%, and your derating factor in this case would be at 26.5%. Again, this has nothing to do with the example, and your total demand will be 40 times 5.5K times 0.265. That will get you a healthy 58.3 kVA. Here's another example for dryers. Another example for dryers. Again, this has nothing to do with the, everybody can I have thumbs up chat? That's not part of the, it's just to get you to do the math. Any comments, guys? Any questions about that? The dryers? This is just applying these rules. Can you guys see that? These rules? Dryers? Okay, so we got the dryers. Let's do the heaters. Now, heating slash cooling. Heating slash cooling, guys, if you go to Article 4, 220.51, section 220.51, It refers you to 440 and 220/60. All these articles will tell you one thing. Pick the largest of heat or cool. So let's go pick the largest of heat or cool. Now remember, these are at 240. The voltage for these babies is 240 volt. Okay. The heat, guys, you guys remember what the heat was? The heat was 10K. Where did 10K come to be? I gave you, it's a 10K. So you take the 10K, multiply it by 30. That will get you a healthy 300 kVA. Then the heat, that's the heat, the cool. The cool is, I have 30 amps, multiply this by 240, because that's my heaters, multiply it by 30 of them, and that will get me a healthy 216 kVA. So these are the heat and the cool. Did you guys hear me, everybody? Then choose the largest. The step that, because these are non-simultaneously used, highly unlikely, Karen, that you're heating and cooling your house at the same time, right? So I would say choose the largest of heating and cooling. The largest of heating and cooling, when you use the largest, guys, obviously cooling, in this case, we are, so AC 30, okay, 216, 240. So in this case would be the heating. Why did I say cooling? Heating. Heating is going to be 300 kVA. And that's the number that I'm going to be using. Did you guys hear me? I don't know why I said cool. Right? You pick, look at these two numbers, and you pick the largest. That's the number that you're going to be using for this step. That's the number that you're going to be using for this step. So what we did, Matt, is we did the 10 kVA heat. I'm giving you that each one of them is 10 multiplied by 30, 300. The cool is 30 amp, 240 each AC. 30 multiplied by 30 because 30 of them give you this number. And then you choose the largest of these two numbers. You choose the largest of these two numbers. Where does it say that? That's in 250.51 or 220.60. 220.60, I believe it says non-coincidental load.
Why didn't you have to multiply the heat by 240?
Because the heat is already given. The way the heat is given, let's go back to the start of the project. If you look at the heat is given in what? Here's my heat. Look at the heat. The AC is giving 30 amp 240. The heat is given 10 kW. It's already given in kW.
Okay. All right.
The AC is given in amps and voltage. I have to multiply them to get the volt amp. The AC is already given in kW, which is volt and amps for the most part for resistive load. Okay, so we got that one heat. Okay, so we got the heat cool. Any question guys about the heat cool before I jump into step number 11? I skipped 10. What's 10 in your schedule, guys? What was 10?
Computing, general lighting, small appliance, laundry.
Yeah, I skipped that one because just adding all this stuff together. I'm going to do it later, okay? I'm going to go fast in place appliances, 220.53. If you, gentlemen, ladies and gentlemen, if you go to section 220.53, it tells you if you have fasten in place appliances, you are to apply a demand factor of 75% demand for these. Okay, so let's go see dishwasher, garbage disposal, and washing. dishwasher, garbage disposal. I have my dishwasher, my garbage disposal. So for dishwasher, guys, here is the calculation for dishwasher. I have 1.2K, multiply this one by 30, and that will give me a healthy, well, we add them all up at the end. So 1.25. Then for this, you're going to take 1.5K multiplied by 30. And for this boy, you're going to take 5K, the heater, water heater, 5K multiplied by 30. You're going to add them up. That will get you 231 kVA. And then you're going to apply the demand. This is step 12. I'm going to have step number 12 in your sheet. Step number 12, guys, in your sheet, to apply the demand, you take the 231K, cut it by 0.75, because 4 or more, you cut by 0.75, will get you 173.3 kVA. That's the demand that you're going to carry. One more time. 1.2 for the dishwasher, 1.5 garbage disposal, 5 for the water heater. Where these numbers come from? The example they gave you. Multiply by 30. Why 30? There's 30 apartments. Then add them up. Then step number 12 in the sheet that I gave you says apply the 0.75 demand on that. Did you guys hear me? So that's what you get. Any comments, any questions, my friends? Any comments, any questions? Any comments, any questions? Karen, are we good with that one? Yes, no? That's step 11. I can't emphasize you guys are following that PDF file that I gave you, as well as this calculation. Hopefully the two will sync together. You do it for the project, and you're going to do it for Chad for the calc, because we test you on it too. Matt, let me know when I can move to next. Move? Okay, good. Let's go to step number 14. So I skipped a couple of steps. Can you guys tell me what was 12? 12, we did it. Well, step 12 was demand. What was step 13, Matt?
Total computed load, adding small blank.
Yeah, total computed load, adding them all up. We want to skip that one. The reason why I want to skip that one, because ultimately the goal, we're going to add them way at the end, right? So motor loads, 220.50 and 430, Article 430. These are your references when it comes to the motor. I have one pump, 7.5 horsepower. That's it. All the motors I have only one pump. Here's what the NEC code book, guys, says. You're going to take that one pump. You guys remember that one? You're going to go to table 430.248, and we did that math under 240 volt. You're going to find 40 amps is the load for this motor. This 7.5 sump pump or pump motor is going to have 40 amps. Cool? Then you take, since it's one motor, 1.25 times the largest motor, it's only one, multiplied by 240 plus all the other motors, which is 0, and that will get you a healthy 12 kW, 12 kVA. That will get you 12 kVA, and that's the load for this one. What's with the 0 here, Matt? If you have another motor, suppose I have another motor, right? We don't have it. I'm going to erase it here. Suppose I have two of them. You take 1.25, multiply it by 40, multiply by 240. What is this, Chad? This is supposed to be 240. 240. Sorry for that. I want to use a different color though, for a reason. 240. Okay. So this is for the first motor plus, right? If you have another motor, don't write this one. If you have another motor, then you take the another 40, the same size, multiplied by 240, equal, and you add them up. Did you guys hear me? That's how we do it if you have different motors. You take the largest motor, multiply by 1.25, multiply by the voltage, 5 volt amps, then add all the other motors to it. Again, we're not doing this step, so I'm going to go erase it. If you guys don't mind, don't do this last step. That's if you have two motors. If you have two pumps, 7.5 each, that's how we do it. How about if you have three? Then you multiply this number by 2. 2 for 2 motors, and that one with the third one. If you have 10 of them, 1 will be represented here, the other 9, this will be multiplied by 9. Okay? So we don't want to confuse you here, so that's motor calculation is coming, guys, for feeders. Okay, so that's my step number 14, my motors. Step number 15 says total all of them. Let's go total. We're going to go total all of these stuff that we have done so far. Okay, here's the total. And this is step 6, 7, 8, 9, 11, and 14. These all steps, guys, I'm going to total them. Okay, so let's go write the total. So I have 70. Do me a favor, when you write them on a piece of paper, guys, leave space here because I want to do the neutral. Can you guys leave space at the end here because I want to do a neutral right on it with a different color in a second here. So that was 70.2K. You guys remember that? And that was 56.3K. That was the range. For the dryer, it was 61.4K. For the heat cool, it was 300K. For the fastening in place was 173.3K. And for the motors, it was at 12K. And guess what we need to do, guys, gentlemen? We need to go add them up. So when you add them up all at the bottom, you're going to end up with a healthy 673.2 kVA. This is ultimately, utterly, how you will be sizing this system. That's that every single electrical load in your building. Add it together. 673.2 kVA. Cool. Any comments, guys? Any questions? See how easy that is? Or how hard that is? Is it hard? Okay. Now when you go, now the goal is to size, again, back to the sizing. I keep collecting these here. The goal, guys, is to size the, number 1 is the panel. Number 2 is overcome protection device. Number 3 is the conductor, the grounding electrode conductor, and the main bonding jumper. I said I'm going to give you guys a copy of this. Should have made you a copy of it. Okay, how about if I make you a copy? You don't have to draw that one. I'll make sure I make you a copy of this. How about that? Cool. I'll make you a copy of this. You don't have to draw the whole thing. I'll make you a colored copy of it. Okay, that's the goal. Is to size. But everybody understand my goal is to size the service coming to this building. Okay, let's go size it. So here's my total load. Now I'm going to go back and size the service. Okay, 16. That was step 16, guys. Service entrance equipment. This is service entrance equipment. We need to size service entrance equipment, overcurrent protection device, and conductors. That's what your goal is, to size the overcurrent protection device, right? Service entrance equipment, and overcurrent protection device, and conductors. 3 things. I can't emphasize, guys, I'm going to get you the sheet in a second here. So let's go do the math first before we go ahead and do it. So then you're going to take I equal 673.2K divided by 240. That will get you a healthy 2805 amp. So you divide the kVA that you came up with, guys. You divide it to find, divide the kVA by the voltage. Okay, then to size the panel and the overcurrent protection device, I need the size of the panel and the size of the overcurrent protection device. Can you guys see that? 1 and 2 are coming from here. Can I get you guys? Here's my 1 right in here, that panel, and 2 is the overcurrent protection device. Can you guys see there? Okay, so everybody can see what 1 and 2. Let's go size. So the panel size, here's what you're going to do. Then you're going to take 2805, go to DeWalt 3-13, 3-13, and you're going to end up with 3000 amp service. You end up with 3000 amp service for this apartment building. 3000 amp service for this apartment building. Based on 2,805 amps. The next standard overcurrent protection device, the next panel, you go to the next standard overcurrent protection device, next standard panel size. Okay, so that's the panel. What is the panel? And what's overcurrent protection? The panel is a box. That's what we're sizing, the box. The overcurrent protection device is the circuit breaker inside the box or outside the box. We can put it typically inside the box, but it could be also outside. And these are 2 different things. You can have a 400 amp panel, guys, with a 200 amp circuit breaker inside or outside it. So there are 2 different things. Okay, panel size. The overcurrent protection device, same thing. For here, for the overcurrent protection device number 2, guys, you take the 2805. You're going to take it to 240.6 NEC code book, and that will get you a healthy 3,000 amp. So I have a 3000 amp panel with a 3000 amp circuit breaker inside it for this apartment building. 3000 amp panel. I believe this is step number 16, isn't it? Looks like 10 here. Step number 16, right? 16 in the sheet will tell you how to size service entrance conductor. Is that, Matt? Yeah, step number 16. Now I size 2 things. I size the panel and I size the overcurrent protection device. Now what's left? I need the conductor. I need to size service entrance conductor, guys. 2 hots. Service entrance conductors, 2 hots. Okay, if you guys go to 240.4c, it says match overcurrent protection device. How do you size a conductor? Match overcurrent protection device. Okay, what size overcurrent protection device do I have? I have a 3000 amp overcurrent protection device. Can you find a conductor for 3000 amps? No. So what do you do if you can't find one conductor that can carry 3000 amps? What do you do? We parallel. The concept of paralleling, guys, is to have 2 conductors. This conductor can carry 100 amp. This conductor can 100 amp on each phase. You tie them at the end like this. So 100 plus 100, 200. Now this system is 200. Say if I need another 100, I grab another conductor in every phase, tie it at the end, They call them parallel. Tie these conductor at the ends. Here's the circuit breaker here. Here's the load. Tie them at the end. Now each one of them is 100. The total would be what? 300. Everybody understand what parallel conductor is? We use them all the time. Typically, we use them if your load is 400 amp or higher, you start parallel. Obviously, my load is way too high than that. So I'm going to go. So how do you hire? Divide this by 10. Why did I divide it by 10? I decided to pull 10 conduits. Why did I decide to pull 2 conduits? I'm going to tell you why. So divide this by 10. That'll give you what? 300 amp. Take this one to table. Take it to table 310. Table. 310.15 B16 under 75 degree column or Celsius. That will give you 2 conductors, number 300 kcm, 350 kcm. Number 350 kcm. 2 conductors, 350 kcm. 2 conductors, 350 kcm. This is the hot conductors. 3 conductors. 3 conductors. 3 conductors. Number 350 kcm. I mean 2 conductors. Okay, here's what paralleling is. Look at this. I drew this one for you guys. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 conduits. Each conduit is going to have 3 conductors. 2 of them are hot and size at 350. The third one is the neutral. We shall size it in a second. One more time. Why did I divide by 10? Could I have divided by 12? Yes. Could I divide by 9? Yes. What's the rule when we parallel? When you parallel, the rule is when you divide by any number, you want to be hovering around 400. That number here, you want it to be around 400. 400 to 300. That's a range that you want. So divide by any number that can get you 300 to 400, because that's the size of the conductors that the best parallel conductors. Give you 500 kcm more or less. Okay, and 10 is easy division. If you take 3, divide this one by 10, give you 300. 300 go to 3, 10 or 15 be 16, give you 3. So can I get you guys to understand? I have 10 conduits. Each one of these conduits, 2 conductors are 250. 2 conductors are 250. 350. 2 conductors. Can you guys see? Here's the hot. The 2 hots are 350. The neutral, you're going to see it's 1 knot. We're going to see the neutral in a second. It's going to be 1 knot. But I'll size the neutral in a second. Before I let go with this. This is, Matt, this is all the steps until you reach the step that says sizing the neutral. Now we're going to go size the neutral. Why 2 conductors, 2 hots? I'm running 24120 single phase. What size neutral we're going to do? We're going to do it in a second. That's the size of the neutral you're going to do. Any comments, any questions? Any comments, guys? Any questions? Now for the neutral, here's how I do the neutral. I'm going to go to every single one of these steps, guys. The steps that we're going to repeat everything that we have done. It's not a whole lot, believe me, to size the neutral. And in the back of your mind, you're going to ask yourself, is this 120? Yup, count for neutral. Is this 240? Drop, unless the code says otherwise. Shall we? Any comments, any questions, guys? We size the 2 hots. We size the 2 hots. Now we need to go do calculation to size the neutral. Do you guys see why are we doing what we're doing right now? To come up with this size. That's what they're paying you to do. To size the service. The panel, and the conductors, and the overconduction device. But the neutral, almost always, the neutral in the building, guys, is smaller conductor-wise than the hots, because the neutral is supposed to carry the unbalanced load between the 2 hots. That's why we have a neutral. So you don't want to, most 99% of the time, the neutral will be lower than the phases at the service, at least at the service. We'll talk about what the best practice for neutral when we go to the commercial too. Okay, I want you guys to go back to the beginning so that we can, everybody knows we're done with the phases. I'm going to go back and size the neutral now. Can you guys back through this sheet that you have? Okay, looking at it. Number one, do you see, guys, the AC unit is at 240. Do you think this is count? This will count for the neutral? AC unit 240. Exit. Can you guys see? You have it right there. X that one on the sheet that you have. Is it going to be in with green? This will not count for a neutral. Heating. Can you guys see the heating is 240? Would it count for a neutral? Exit. No. Ranges at 240. Ranges, the code says they count. They are 240. Actually, typically they are 240/120. 240/120. Can you guys write next to them 240/120? So they will count. The dryers. How about the garbage disposal? Would the garbage disposal, guys, count for the neutral? Yep, it's 120. It will. How about the pump? Would the pump count for the neutral? It's 240 only. Would it? No. Cross it. Water heater. Would it count for the neutral? No. Why? 240. It doesn't have a neutral in it. Dishwasher? Yes. Can you guys do me a favor? Go literally X these loads because they will not count towards your neutral. Why? Because they're 240 only. There is no 120. Okay, now let's go repeat. Now I'm going to go repeat the steps. Okay, so for general lighting and receptacles, I'm going to ask you, are all the receptacles analyzed connected 120? Yes. Would they count for the neutral? Yes. So repeat step 1, 3, 4, continue. That's going to continue. And the small appliances, are the small appliances 120S? How about the laundry? 120S. So all these guys are going to continue the same, all the way up to the demand. So this value here, when you go to step number 6, please, go to step number 6. Do you see that number here? The same number, I'm going to call it neutral here, and for neutral, the neutral, exactly the same calculation, is going to be 70.2 kVA. Can you guys just write in step number 6, right next to step number 6, write N 70.2 kVA. No, the same calculation. Can I have thumbs up that same calculation for neutral? Why? Why? Because it's all 120 loads, receptacles and lights. So right at step number, that's why I have this green here next to it, guys. So step number 6, right, step number 6, please, 70, N for the neutral. Can I have thumbs up, chat? We got that one? Adam, Karen, okay. Now we're done with this. Okay, move on to ranges. For ranges, go to step number 7, please, ranges. For ranges, then you see code book, guys, for ranges say, take 75% of, for calculating the neutral size, 75%. You guys did it with me, 75%. So for neutral calculation, right here at step number 7, right, big N, and sizing N, you take the same number, 56.3, multiply it by 0.7. Why 0.7? Because the NDC code book came up with 0.7, and you end up with 39.9 kVA. Can you guys write me for step number 7, when you size a neutral, that's how much you're going to size a neutral. Even though ranges are 240, 120, because they have 120 with them, they want to accommodate 0.7, 70% of them will be counted towards a neutral. Where did the 70% came to be, guys? Directly from 220.55. 220.55.
I got 39, 410 for that one.
39 point what? 375. Okay, maybe it's the approximation that we're doing. Okay, so what would that? One more time. 56.3 times 0.7 is what? Okay, so we're 59 point. One more time. 375.4. How about that? Approximate. Okay.
That's what I got. I got 39.4.
Thank you. Okay. I think I probably, when I did the math approximation, when we did it, Okay, 39.4 kVA. Okay. Everybody got that one? Let me see. Remind me to change it in my total because I need to change it. It's not going to make a difference in my total. 39.4. Okay, now let's go to step number 7. Step number 8. Dryers. Go to step number 8. Dryers. Same thing. We at the bottom, guys, put N for neutral. And for sizing the dryers, 61 point, the same number that we have here, 61.4 K. Multiply this one by 0.7. That will get you 43. Can you guys check my math? 43? Okay. Why do I multiply by 0.7? 220.61b, 220.61b for dryers and ranges. For dryers and ranges, it will tell you when you size the feeders, 220.60b. For dryers and ranges, when you size the feeders, take them at 75% neutral-wise. Neutral-wise. Because they are 240, 120. They have a 120. Typically, the dryers, they run the motor in the dryer, the electric dryer at 120, and the heating elements at 240. Okay, everybody understand why we did that? And here's your reference, guys. 220.61b is the reference for the neutral. Okay, so let's go directly into, we don't want the extra heating. Okay, let's go step number 9, heat. I want you guys to look at the heat 240, AC 240. Do they count for neutral? No. So what do you need to do right in here? I would like you guys to put an N, circle it, and so for yourself, so you know that you accommodated for this. Can you guys see this big fat 0? And put big fat 0. Why do I do it this way, guys? Then Adam, as you review your work, you know, yeah, you looked at this step and it's 0, it doesn't count. Does that make sense? Okay, so now they don't count towards a neutral, and I know. How about fasten in place appliances? Okay, how many of them? I have dishwasher and garbage disposal. How about that water heater? Okay, so now I need to do math here. Can you guys go right next to it? You have to do 1.2 K times 30. Here you're going to have to 1.5 K times 30 units. Here you're going to have 0 times 30. Why 0? The water heater guys are 240. So when you add them up, you're going to end up with 81 kVA. Then you have to apply the demand factor on them right here. You take the 81 kVA times 0.75, and that will get you a healthy 61 that'll get you 61 kVA. One more time. I did the math exactly like I did for the phases, except I dropped, the only one that I dropped is what? The water heater. Why did I drop the water heater? Because it's running at 240. It will not count towards my neutral. Would it? Would it? Because the code says 220 at 53 says 0.75, exactly like the phase, right above it. 0.75. The neutral is 120. You can see how when you put it on the same sheet, it makes sense. You're doing the same calculation for neutral. You're asking yourself, oops, does it count or doesn't it count? And based on the code, everything is based on the code. Like why did, like you said, the 0.75 is for the phases. The only thing different that I did here, the 120, I counted them right here. The 240, I zeroed them. Can I have thumbs up, Chad? We fully understand that one? Okay. So let's go to next step. Motors. Anybody can guess the motors? Can you guys guess what the neutral for the motor will be? And do you see it's a 240? Do you see any 124 motors? Would they contribute to the neutral? No. So what would that be? Big fat fluffy 0. So the neutral for the number for step 14 will be 0. Let's go to step 15, which is the last, adding them up. Step 15, can you guys see? Now we're going to add them up. Look at that. I'm going to add them up right on the other side, guys, in green. Exactly the same steps. So for step number 6, it stayed the same, guys. It has 70.2K. For step number 7, 30, which one did we change? Was it 39? 39.4K, right? Is that the step that we changed? 39.4K? Okay. Actually, it was 39. I just, because I have it here 39, I think I wrote it. Looks like 9. I mean 39.4, but I wrote it like 39.9. It's just my right. Yeah, you're right. Okay, so 40, this is for step number 8. If you guys go back, this becomes 43K. This becomes big fat fluffy 0K. This is 61K. This for the motors, big fat fluffy 0K. Add them up. Same thing, you're gonna add them up. When you add them up, you're gonna end up with 214 kVA. That's your total for your neutral. That's 214. 214 kVA, that's your total for neutral. Can you guys assure me that you know that we have just repeated all these steps for the neutral, right? Same steps. Redundancy. Okay? Everybody knows how we came up with 214 kVA? Did you come up with 214? Okay. So I was not sleeping. Now this is the number 673.2 kVA is the one that we use for phases. That's the one that we're going to use for neutral now. 1/3 almost. Can you guys see it's almost 1/3? What happened to the rest of them? They're 240. They're not seen by the neutral. Okay, now we're going to go back and size the neutral. Number 4. Can you guys see that? Number 4. I'm sorry, not the neutral. Yeah, number 4. We're going to size the neutral. Number 4. So let's go size the neutral. Go back. Okay, so here's my overcompression device. I'm going to go back. Now I know what the load is. I'm going to go size my neutral. Okay, right here. Can you guys write here, put 4, step number 4. I'm putting it in green because it's neutral. Take the 114, divide it by 240. Why 240? Even it's a neutral. Why do we divide it by 240, Matt? It's even it's neutral because you're balancing the neutral load between the two halves. Typically 50-50 on each leg. Okay? So that will give you guys 892 amps. That's how much amps you have. Now, then you're going to do the same thing. This is step 1. You're going to take the, then from here, you're going to take the 892 divided by 10. I need somebody to tell me why did I divide it by 10? The phases were parallel 10. The neutral have to be parallel 10. Yes. Yeah, because if you're running them in conduits, every conduit is going to have a neutral. So that will get you an 89.2 amps. Okay? And then if you take the 89.2 amps, take it to table 310.15 B16 under 75-degree column because the equipment is rated for more than 100 amp. That will get you how many conductors? One conductor, number what? Number 3 AWG. Okay. Now we have a little problem here. Look, up to this point you're done. You're done. But there's one little problem. The NDC code book, guys, tells you you shall not, will not parallel less than 1 knot. Am I paralleling? Can I parallel number 3? No. If it's one conductor number 3, it's okay. But if you are to put two conductors number 3 like this, you cannot. They don't want you to parallel. Requirement. The smallest conductor that you want, the smallest conductor that you can parallel by code is 1 ohm. So what are you going to do then? Up that baby into what size? 1 ohm. So this becomes, but everybody knows why? This becomes one conductor number 1 at AWG. Everybody knows why? Because we cannot parallel less than 1 ohm. So here's your 10 conduits. This is my conduit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's my 10 conduits. Each one of these conduits is carrying 350 kcm, conductor, 2 conductors 350 kcm, and 1 conductor 1 ohm. Can I have thumbs up, Chad? That's how they bring the apartments downtown Minneapolis, how they wire them. Any comments, any questions? Let's go size the conduit for that baby, huh? Let's use THH, and I'm going to use my calculator here quick. You guys know because you need to size the conduits. For you, you're going to do the math. For Chad, he shall use the calculator. So here's my calculator. Let's go directly into this. Okay, size. Let's go medium. Okay, so let's go set my calculator, set 75. It's set at 75. Okay. 350, right? I have 350, guys. I need to go set my calculator to PVC first. Shall we see what's the setup for PVC is? It says when you set your calculator for PVC, it has to be 9. PVC 80 is 9. So I'm going to go set it. I hit 9, set, and conduit. I changed it to PVC schedule 80. Why? If you're doing service that large, typically we put them in PVC schedule 80 underground. Cool? All right, so let's go 350. So here's my 350. My 350, here's my K, wire size. What size? How many of them? 2 of them. What type of insulation? We're using THHW here. Click on that. Then 1 aught, here's 0. Here's the wire size. How many of the 1 aught do I have? 1. 1. What insulation? THHW. Here's your total, cubic inches, square inches, and here's your conduit size, 2.5. So that's my conduit size, 2.5 PVC schedule 80. So if I did everything right, then I'm going to go to here. See how easy if we did. So each one of them is going to be 2.5 inch PVC schedule 80. That's what you guys at the end, Matt, when we're at the end of that 4 sheets, you are to size the conduit. You're going to go to, you guys don't have a calculator, you're going to do it by hand like I showed you. To calculation cross-sectional area, table 4, table 5, and you size your conduits. You size your conduits. Any comments, guys? Any questions about the load calculation? This is one of 3 load calculation you're going to do, Chad. One will be residential for apartments. The other one we're going to do commercial next in a couple of weeks, and the third one for industrial. Same concept. You understand it now, you're good to go. You don't understand it now, how many shots you have at it? 2 more shots. Okay. The last thing I want to do, guys, is for the neutral. Back to the neutral. For the neutral, I don't want to get into the main bonding jumper and system bonding jumper. There's something called, I just have to go back to my graphic here. Okay. In the US, which we are in the US, when you bring the neutral to the service, I'm sure you guys, the ones who finished with electrical, that you did that one. The code require you to bond the neutral that you're bringing from Xcel Energy into the grounding electrode conductor. So what they do, Matt, is they take the neutral, they tie it to a wire, and they take it to the ground right at the premises that you are bringing the service to. It's required by code. This bonding jumper, this is called system bonding jumper. That wire here, the green wire, is called the system bonding jumper. And I promise we're going to go over this in details when we go to commercial industrial. So we will do it. This is system bonding jumper. So this is that wire. Let me just go back again, size that. This one here is called system bonding jumper. This wire here is called grounding electrode conductor. Grounding electrode conductor. That's the wire that you take to the ground rod and tie to the ground rod, or to the steel, or to the water. I have a whole grounding and bonding for you guys in industrial, more than you can ever imagine. So we'll go this into details. But for the time being, remember, the service panel you must bond the neutral to the ground. You have a conductor coming from the ground bar. There will be a bar, grounding bar inside your panel. You take a wire from it, take it to the ground rod, a rod into the ground, and then you tie the ground bar and the neutral bar, two bars like this, inside your panel, one neutral, one ground, and you go and tie them with a wire. Tie the two together. That's called main bonding jumper. Why do I bring it here? Not to confuse you. So here's how they size the system. 10 sets, two 350 kcm THW, and one out AWT. That's what you're going to size for me. Now, we size the neutral. We're already done with the neutral. But there's one check you have to do. One little check. Your neutral that you size here must not be smaller than the main bonding jumper. That's what the code says. No matter what you come up with neutral-wise, it shall not be smaller than 1 aught. If your pedal is smaller than 1 aught, but also it cannot be smaller than the main bonding jumper. So let's go size the main bonding jumper and check. Is the neutral smaller than 1 aught, than the main bonding jumper or not? Okay? So let's go to this one. I have the last thing. Here you go. Main bonding jumper. If you don't, here's where 250.24C1, that's where it tells you guys that the neutral cannot be smaller than the main bonding jumper. Everybody knows what the main bonding jumper? A wire tie the neutral to the ground bars inside the panel. That's called main bonding jumper. Fancy name. Okay, how do you size the main bonding jumper? If you guys go to table 250.66, not 250.66, it'll tell you if it's larger than, and if you go to 250.28, it will tell you to do the following. Number one, how many sets did we pedal? 10 sets. We pedal 10 sets. Multiply it by 350K. That will get you 3500 kcm, right? Why did I multiply? This is the size kcm. This is the size of the conductor, the service conductor. Where does the 10 come from? Because each one of these conductors actually has 10 in it. Then you take 12.5% and 12.5%. Where the heck is the 12.5% came to be? 250.28. 12.5%. Multiply it by 3500 kcm. That will get you a healthy 438 kcm. 438 kcm. Okay, then you take the 438 kcm, you take it to table number 8, chapter number 9. That'll get you a 1500 kcm. So your neutral, the equivalent of your neutral cannot be smaller. The equivalent of all your neutral cannot be smaller than 500 kcm, right? The equivalent of my neutral cannot be smaller than 500 kcm. Now let me ask you, what was the size of a neutral that we did? 1 aught. How many of them? 10. Are 10 aught, 1 aught bigger than 500 kcm? How do I know, Chad? You're looking at apples and oranges. How do you convert them so you can see which one of them is bigger? What's a 1 aught? How do you convert 1 aught into kcm so you can look at apples to apples? If it was 250, if I tell you, Is 400 kcm larger than 500 kcm? No. Have you lost it, Chad? If I tell you, is 1 aught larger than 500 kcm? Do you know? No. Well, I know it's smaller, but I don't. But how about 10 of them? So in order to compare apples to apples, here's what you need to do. Okay, so the last step, guys, you need to compare is here. You take the 10 sets multiplied by this number, 1, 0, 5, 6. Is that 8? Oh, no, that's 5, 6. Okay, 0, 1, 0, 5, 6, 0, 0. And that will get you 1, 0, 5, 6 kcm. 1056 kcm. Now, where did that number came to be? What the heck is this? This is your 1 at AWG from table number 8, chapter number 9. When you go to table 8, chapter 9, guys, a 1 at is equivalent to 105600 cm. Did you guys hear me? cm. So now, Karen, you can look at, is the 1056 kcm smaller than 500 kcm? Obviously not. Can you guys see that? Everybody can see that? Then you compare these two numbers. That now we're talking about apples to apples. 500 kcm and 1056 kcm. Which one of them is the largest? The bottom one, Chad. Then this was your minimum. Am I less than 500 kcm? No, I'm good to go. That's the check that you do for your neutral. If your calculation here, guys, end up with 350, that bottom one here, then you have to go back to 500 kcm. But because we're paralleling, most likely when you parallel, you don't get into this situation. That's all I have for you guys. Any comments, any questions? I know it's a lot for Monday, huh? But we'll take you a few things to digest over it. This is the bread and the butter, what we do. So back to what we did here, guys. Now, here's my 500 kcm, the main bonding jumper, or the system. Actually, it's not system here, I'm sorry. This is main bonding jumper. The main bonding jumper, right bond the neutral. The system is for subdivided system. Main bonding jumper right here, 500 kcm. We will get into sizing the grounding electrode conductor and so forth, guys, later on. Any comments, any questions? Any comments, any questions? Okay, I'll make sure I make a copy of this, and I'll give you a copy of that graphic, and that's all I have. Thank you.